Picture this. A spot on our planet where gravity takes a little nap, a region in the Indian Ocean where its grip is noticeably weaker. Not enough to make things float upwards or anything dramatic like that, but enough to create this subtle dip in Earth's gravitational field, like a tiny gravitational dimple.
It truly makes you reconsider how we think about gravity, doesn't it? We tend to imagine it as this unwavering constant force.
Exactly.
But in reality, our planet is far from a perfectly smooth sphere. It's, think of it more like a slightly lumpy potato.
A potato Earth. I like that.
Yeah, and these variations in how dense different parts of the Earth are, they mean that the gravitational pull isn't uniform across the globe.
Right. And this potato shape leads to something called a geoid. It's a bit technical, but imagine if all the water on Earth were perfectly still, only influenced by gravity and the planet's spin.
Okay.
The shape that water would take, that undulating uneven surface is the geoid, it perfectly shows how mass, and therefore gravity, is distributed unevenly. So our mission today is to, dive deep into this gravity anomaly in the Indian Ocean and unpack what recent scientific explorations are revealing about this fascinating puzzle.
And a puzzle it has been for quite some time. This gravitational dip, it spans over 1 million square miles. It's huge.
Yeah, 1 million square miles.
Yeah, and what's particularly intriguing is that the ocean floor in this area is actually lower, and sea levels are reduced there too. It's almost as if the water itself is feeling a gentler pull.
Which just begs the question, why? I mean, what could cause gravity to be weaker in that specific spot?
Well, initially the answer really eluded scientists. It wasn't obvious at all. But that's when some serious scientific sleuthing began.
Okay.
You had 2 Indian researchers who decided to look back, way back into the past, to find some clues.
How'd they do that? Time machine.
Not quite. Their approach was quite clever, actually. They used sophisticated computer models to simulate a virtual Earth, essentially rewinding the geological clock and peering down, like 620 miles beneath the surface. These models let them simulate how temperature and density variations deep inside Earth would have influenced rock movement over millions of years.
So they're running Earth's history on a computer.
Pretty much, yeah. And their initial thought, their first hypothesis, focused on a major geological event around 30 million years ago.
Okay, what happened then?
Well, their idea was that a chunk of ancient ocean floor sank deep into the Earth's mantle. This massive sinking event, they thought, could have caused hot molten rock to sort of slosh around down there. And this movement, they proposed, might have subtly weakened gravity in that particular area. It's a compelling early idea, definitely. But the story evolves.
Okay, so that was one theory, but things moved on.
They did. Fast forward to 2018, and a team of Indian scientists took a more, let's say, direct investigative route. They actually went out into the Indian Ocean.
Boots on the ground, or rather ships on the water.
Exactly. With incredibly sensitive instruments designed to essentially listen to the rumblings within the Earth. Think of it like using a stethoscope on the planet.
Listening to the Earth's heartbeat.
Kind of, yeah. These instruments collect data on seismic waves, the vibrations traveling through the Earth.
And what did they hear? Anything interesting?
Oh, yeah. It turned out there were plumes, actual streams of hot molten rock rising upwards from deep within the Earth.
Whoa. Okay, so not just sinking stuff, but rising stuff too.
Precisely. This discovery added another really important piece to the puzzle. Could these upwelling streams of superheated rock also be contributing to the reduced gravitational pull?
It complicates things, doesn't it?
It certainly paints a picture of a much more dynamic and active region beneath the Indian Ocean than maybe previously thought. But to really grasp the potential causes, we need to zoom out even further, geologically speaking.
How far back are we talking now?
All the way back to about 140 million years ago, back when the Earth's continents were mostly joined together in that supercontinent, Gondwana.
Right, Gondwana. I remember that. India was part of it.
Exactly. And as India began its long northward journey, breaking away from Gondwana, something else significant happened. The floor of an ancient ocean called the Tethys Sea.
Tethys Sea, okay.
It started to slide beneath the Earth's crust as India moved north. It got subducted.
And this links back to those computer models.
It does. This is where our 2 Indian researchers continued their virtual time-traveling experiments. They kept digging into the data. They refined their computer simulations, meticulously tracking the movement of both the land masses and the Earth's mantle, that thick layer of hot, solid rock beneath the crust.
So more detailed simulations.
Right. And this deeper dive into Earth's history led them to a more nuanced and detailed theory.
Okay, let's hear it. What's the latest thinking?
Their refined theory is that way back when, hot, less dense rocks began ascending from deep within the Earth.
Ah, so the rising plumes again.
Yes, but linked to that sinking Tethys floor. These buoyant rocks, they suggest, are what created the weak gravity spot, because this hot, molten rock is generally less dense than the surrounding cooler material.
Right, less mass in the same volume.
Exactly. Its presence can slightly reduce the overall mass in that specific column beneath the Indian Ocean, leading to that subtle weakening of gravity we see at the surface. Essentially, it formed a big dent in the geoid and on the ocean floor.
A dent caused by rising hot rock.
Interesting. Is there a timeline for this?
Well, what's particularly interesting is the timeline they've managed to piece together. They estimate the first of these rising rock formations appeared around 20 million years ago.
20 million, okay.
And initially, it was south of where we see the gravity dent today. But as these buoyant materials continued to move upwards and eventually spread out beneath the crust, the gravity dent grew larger and its effect became more pronounced.
So it wasn't an instant thing. It developed over millions of years.
Absolutely. They kind of envision these rising rocks being pushed upwards, almost like bubbles forming. Bubbles pushed up by what?
By the dense, sinking remnants of that old Tethys seafloor. It's this incredible image of these immense geological forces interacting, sinking cold stuff, pushing up hot stuff.
Wow. That's quite a dynamic picture deep beneath the ocean.
It is. And this process might even involve what scientists call the African blob and the Pacific blob.
Blobs, like actual blobs.
Well, sort of. They're these colossal formations of rock deep within the Earth's mantle. We're talking structures on the scale of continents extending almost halfway to the Earth's center.
That's enormous.
Huge. And scientists believe these blobs might be the source regions, the origins, for these columns of hot rock, these plumes that rise up.
Okay.
And these plumes can trigger major volcanic eruptions at the surface. Some even hypothesize a link between disturbances in these blobs and past extinction events, like maybe the one that wiped out the dinosaurs.
Seriously, so these deep Earth blobs could be linked to surface catastrophes.
It's a major area of research. The potential link between these deep-seated structures and surface events really underscores how interconnected Earth's systems are across vast depths and timescales. So any disturbance to these blobs or plumes coming from them is potentially very significant.
Which certainly adds another layer of intrigue, maybe even a bit of danger, to this whole gravity anomaly story.
It does. However, it's really important to remember this rising rock theory, while compelling, isn't universally accepted just yet. Not everyone's convinced.
Right. Science needs more proof.
Exactly. The scientific process thrives on questioning, on skepticism, and the need for more supporting evidence to definitively connect these deep Earth processes to the gravity hole we observe.
So how do they get more proof? Keep listening.
That's right. Continued investigation is absolutely key. That's why listening to the Earth's subtle rumblings, the seismic data, remains a crucial way to gather more information and potentially solidify or refine the existing theories.
And this hole isn't necessarily permanent, right?
Probably not on geological timescales. We're talking incredibly long periods. This gravity hole might change in strength or even shift its location over hundreds of millions of years as the distribution of mass within the Earth continues to change. Earth is always rearranging its furniture, so to speak.
That long-term perspective really makes you think about how dynamic our planet is.
Yeah.
Constantly changing.
Definitely.
And speaking of surprising planetary stuff, there are other seemingly gravity-defying occurrences around the world that have also puzzled scientists, haven't there? They highlight how important it is to investigate properly.
Oh, absolutely. Like, take rocks that float. It just sounds wrong, doesn't it?
Yeah, rocks sink. That's what they do.
Usually.
Yeah.
But there are types of volcanic rock, pumice is the famous one, that are incredibly light and porous, just full of tiny air pockets from the volcanic gases.
Ah, okay. Like foamy rock.
Exactly. This low density, combined with the effect of surface tension, that sort of thin film on the water's surface, it allows them to float, sometimes for thousands of miles.
Thousands of miles. It's like a geological message in a bottle drifting across the ocean.
It really is. And these floating rocks aren't just a strange curiosity. They can actually help scientists track underwater volcanic eruptions they might not otherwise detect.
Oh, interesting.
Plus, they can act as tiny rafts, potentially transporting microscopic life across vast ocean distances, spreading life around.
Wow. Okay, floating rocks make sense now. What about those moving rocks in Death Valley? That always seemed weird.
Ah, the sailing stones of Racetrack Playa. Yes. That was a fantastic mystery. For over 60 years, these large rocks, some quite heavy, were found with trails behind them on the dry lake bed. It looked like they were moving on their own.
Yeah, I remember seeing pictures. Spooky. People must have had some wild theories.
Oh, absolutely. Ghosts, magnetic fields, aliens, you name it. But thankfully, science eventually provided a more terrestrial explanation.
Okay, what was it?
After decades of investigation, including, placing GPS trackers and cameras out there in that really harsh environment, scientists figured it out. It takes a very specific set of conditions.
Like what?
You need rain to form a shallow pond, then cold temperatures to create a thin layer of ice overnight, maybe just a few millimeters thick. Then as the sun comes up and starts to melt the ice, light winds.
Just light winds?
Yeah, just light winds are enough to push these large, thin sheets of ice. And the rocks frozen into the ice get carried along, scraping the mud underneath and leaving those trails.
Ice and wind. So simple, yet it took so long to figure out.
It did. And what's fascinating is to consider that similar conditions, maybe involving different kinds of ice, might even exist on Saturn's moon Titan. Titan has lakes of liquid methane and ethane.
Huh. So studying Death Valley helps us think about moons of Saturn.
Potentially, yes. Studying these earthly phenomena can offer really valuable insights into processes happening on other worlds.
Okay, another weird one. What about that reverse waterfall in England? I've seen videos. The water definitely looks like it's going up.
Right. It looks incredibly strange, like gravity has just switched off there.
So is that a gravity thing?
No, not at all. As is often the case with these things, the explanation is much simpler, though still impressive. It's caused by exceptionally strong winds blowing up the cliff face.
The wind again.
Exactly. The wind catches the falling water and literally pushes it back upwards, creating that visual illusion of an upward flow. It's pure aerodynamics.
Okay, that makes sense. And isn't there something similar at the Hoover Dam?
Yes, very similar effect. If you stand near the top of the dam wall and pour water out, say from a bottle, it doesn't fall straight down like you'd expect. The sheer size and shape of the dam create a really strong updraft, a current of air rising up the face. And that airflow is strong enough to blow the water upwards.
So again, it looks like gravity is weird, but it's actually just air movement.
Precisely. These examples, while visually striking and fun, serve as a good reminder. While things might sometimes appear as if gravity is behaving strangely, there's usually a logical, often wind-related or buoyancy-related explanation.
Right.
And, we remain hopeful that continued research, more listening, more modeling, will eventually provide that definitive, logical explanation for the fascinating gravity hole in the Indian Ocean.
Okay, so to sort of bring our deep dive to a close then, we've explored this remarkable area in the Indian Ocean where gravity exerts a slightly weaker pull. It's a real thing.
A geoid low.
And we've examined the leading scientific theories which point towards these, immense geological events deep in the past, the sinking of an old ocean floor.
The Tethys Sea.
Right, and the potential rise of hot, buoyant rock from deep within the Earth as key contributing factors. Plumes may be linked to those deep blobs.
That seems to be the front-running idea, yes.
And we've seen that while some phenomena around the world might look like gravity's taking a break, like floating rocks or reverse waterfalls, there are typically sound scientific reasons behind them.
Yeah, usually physics we understand, just applied in an unusual setting.
Which suggests that even seemingly stable aspects of our planet, like, the ocean floor's depths or the strength of gravity in a certain place, are actually subject to these immense long-term internal forces. They're constantly reshaping our world in subtle but significant ways.
Absolutely. And this raises a compelling question, maybe, for you listening. What other hidden processes might be at play, shaping our planet in ways we don't yet fully understand? How might studying these apparent anomalies, whether it's a dip in gravity or those floating rocks or the moving stones, how might that lead to even deeper insights? Not just about the workings of our own world, but perhaps even about worlds beyond our own.
It really highlights that our planet is this dynamic, constantly evolving system, doesn't it? Full of mysteries just waiting to be uncovered.
Exactly. It really prompts further exploration and just sheer curiosity about the ground beneath our feet or beneath the oceans.